The curiosity and imagination of scientists, philosophers, and thinkers alike have driven humanity for centuries. The quest to understand our place in the universe is as old as civilization itself, and it continues to inspire countless individuals to look up at the night sky with wonder. Recently, a groundbreaking instrument has been launched into orbit to help answer this question, the James Webb Space Telescope, JWST. This remarkable piece of technology acts as a powerful magnifying glass, providing unprecedented clarity in revealing the intricate details of distant planets and celestial bodies. The JWST is not just another telescope. It represents a leap forward in our ability to explore the universe. With its advanced capabilities, it can observe the universe in ways that were previously unimaginable. One of the most exciting discoveries made by the JWST is its investigation of an enigmatic exoplanet known as K2-18b. Initial observations of this planet sparked waves of excitement within the scientific community, and with good reason. K2-18b is no ordinary planet. It possesses some truly fascinating characteristics that make it an intriguing subject to study. The discovery that K2-18b contains water vapor has profound implications for its potential to harbor life. Water is considered a fundamental requirement for life as we know it, and its presence in the atmosphere of K2-18b has caused scientists to wonder if this distant planet could be habitable. But that's not all. The planet also contains a molecule that has sparked deep intrigue among researchers. This molecule, often associated with biological processes on Earth, raises the possibility that K2-18b could support life. Could this be the momentous revelation humanity has been waiting for? Could we have discovered evidence of extraterrestrial life? In this exploration, we will dive deeper into the details of K2-18b, examining the scientific challenges and far-reaching implications of this discovery. Join us as we investigate the first tangible images of K2-18b and the potential it holds for reshaping our understanding of the universe. Located 120 light-years away, K2-18b is classified as a super-Earth in its solar system. It stands out due to its classification as a sub-Neptune. This means the planet is larger than Earth, but smaller than Neptune. The sub-Neptune classification does not have any direct counterparts in our own solar system, making K2-18b an intriguing subject for scientists to study. The unique characteristics of K2-18b present a considerable challenge for scientists trying to unravel its mysteries. While rocky planets like Earth and Mars serve as benchmark planets for building hypotheses, and gas giants like Jupiter and Saturn offer tentative comparisons for understanding distant worlds, the sub-Neptunes like K2-18b have no direct analogs, making them an enigma that requires further investigation. The available data so far suggests some fascinating theories. For instance, K2-18b orbits in the habitable zone of its host star, a red dwarf known as K2-18. This positioning raises a possibility that the planet's surface might harbor liquid water similar to Earth's oceans. However, it is important to note that K2-18b orbits its star much closer than Earth orbits the Sun. While Earth is about 1 astronomical unit, AU, from the Sun, K2-18b is only 0.18 astronomical units from its star, which is closer than Mercury's orbit around the Sun. This means that a year on K2-18b lasts only 13 Earth days. Fortunately, K2-18b's host star, K2-18, is a red dwarf that emits less heat than our Sun. This is crucial because it means that, despite the planet's proximity to its star, its surface isn't completely scorched. In fact, this lower luminosity could turn out to be a benefit, as it has allowed scientists to detect vaporized water in the planet's atmosphere. This discovery adds to the growing evidence that K2-18b might just have the conditions necessary to support life. The discovery of biological signatures on K2-18b further intensifies excitement. Methane, a molecule that decomposes rapidly under solar radiation, was detected alongside carbon dioxide, a more common component of planetary atmospheres. However, the most remarkable finding came in the form of dimethyl sulfide DMS, a molecule that is not commonly found in Earth's natural environment. DMS is produced exclusively through biological processes on Earth, particularly by microorganisms in the oceans. This is significant because on Earth, DMS is a reliable biomarker for life. Its presence in the atmosphere of K2-18b suggests that there could be biological processes occurring on the planet. The fact that K2-18b is orbiting a red dwarf star known for its intense radiation and generally considered inhospitable to life only makes this discovery more intriguing. To further understand the planet, it's important to know that for K2-18b to support liquid water, it must reside within the habitable zone of its star, where temperatures are neither too hot nor too cold. If it has a stable atmosphere, K2-18b could have temperatures comparable to Earth's. However, its atmosphere, primarily composed of hydrogen, might make its oceans slightly warmer. Given its proximity to the host star, K2-18b could also benefit from a dense atmosphere that traps heat, preventing surface water from evaporating. This feature is particularly significant because surface water is considered a potential distinguishing characteristic of exoplanets like K2-18b. Astrophysicist Niku Madhusudan, known for his work on DMS in space, proposed a new category of exoplanets in a fascinating paper published in the Astrophysical Journal. He coined the term Hycean, hydrogen-rich exoplanets in cloud, referring to sub-Neptunes like K2-18b that are cradled beneath thick hydrogen-rich atmospheres. According to Madhusudan, these planets could be radically different from anything we've seen before. Hycean worlds could have masses up to 10 times that of Earth and radii twice as large. However, instead of being scorched infernos, they would feature a colossal layer of water, potentially making up as much as 90% of the planet's mass. These dense atmospheres could trap heat from a star, allowing liquid water to exist over a much broader range of distances from the star than on rocky planets like Earth. What makes Hycean planets like K2-18b particularly interesting is their potential for basic microbial life. If these planets exist, they will offer a vast ocean that could harbor the ingredients necessary for life. Their relative commonality in the universe makes them prime candidates for the search for life beyond Earth. Even with the advanced technology of the James Webb Space Telescope, detecting the oceanic features of K2-18b presents a significant challenge. In order to unlock the secrets of this distant world, a meticulously planned observation was required. Scientists needed to observe K2-18b during a transit, a celestial event in which a planet passes directly between its star and Earth. During the transit, the JWST captured the light passing through K2-18b's atmosphere. The beauty of this technique lies in the unique fingerprint that the starlight carries. By analyzing this fingerprint, scientists can determine the elemental composition of the planet's atmosphere. This allows them to identify the molecules present and gain insight into the planet's environment. The light is separated into its individual wavelengths, much like how a prism breaks down white light into a spectrum. If certain wavelengths are missing from the final spectrum, it provides important clues about the chemical composition of the distant world. This method is an invaluable tool for scientists, enabling them to form a complete picture of the planet's environment. The JWST's ability to analyze the atmosphere of K2-18b is a testament to the advancements in technology that allow us to explore the universe in greater detail than ever before. In conclusion, the discovery of K2-18b by the James Webb Space Telescope has opened up new possibilities in our search for life beyond Earth. The presence of water vapor, biological markers, and the planet's unique atmospheric conditions make it a fascinating candidate for future study. The potential for life on K2-18b challenges our understanding of the universe and pushes the boundaries of what we know about habitable environments. As we continue to explore the cosmos, the questions of existence and life beyond our planet remain at the forefront of human curiosity and scientific endeavor. This extraordinary journey into mysteries of K2-18b and the capabilities of the James Webb Space Telescope represents not only a technical milestone, but a continuation of humanity's timeless pursuit of cosmic understanding. From the earliest days of civilization, people have gazed up at the night sky, crafting myths, calculating celestial movements, and gradually refining their tools to decode the heavens. Ancient Babylonian astronomers documented the motion of planets. Greek philosophers pondered the nature of the cosmos. And over the centuries, scientific pioneers like Galileo, Newton, and Hubble revolutionized our grasp of the universe's structure. The JWST, a culmination of decades of astronomical progress, stands at the frontier of this continuum, delivering observations with sensitivity and resolution that previous generations could scarcely imagine. Its mission is not only to explore familiar stellar objects, but to peer into the vast unknown, to study the birth of galaxies, the atmospheres of exoplanets, and perhaps even to detect signs of life beyond our world. The discovery of K2-18b's intriguing atmosphere, for example, would have been impossible without the JWST's suite of highly specialized instruments. It carries a near-infrared camera and IR cam, a mid-infrared instrument MIRI, and a near-infrared spectrograph and IR spec, each fine-tuned to detect the faint signals of light emitted or filtered by distant planetary atmospheres. These instruments allow scientists to perform transit spectroscopy, the same method used to detect the fingerprints of various molecules in K2-18b's gaseous envelope. When the planet passes in front of its star, the star's light filters through the thin slice of atmosphere that rings the planet. Molecules in that atmosphere absorb light at specific wavelengths, creating a spectral signature that scientists can decode to learn what gases are present. This technique is not new, but the precision with which JWST performs it represents an enormous leap forward in observational astronomy. Beyond the specific marvels of K2-18b, the broader implications of JWST's atmospheric analysis open doors to entirely new categories of planetary science. Scientists now speak confidently about characterizing exoplanetic climates, a concept once confined to science fiction. The identification of water vapor, carbon dioxide, methane, and dimethyl sulfide DMS on K2-18b marks a breakthrough that has energized the exoplanetary research community. For the first time, we are not just guessing about what these alien worlds might be like. We are beginning to know. The detection of DMS in particular stands out as one of the most tantalizing findings. On Earth, DMS is a byproduct of marine plankton, single-celled organisms that play a key role in the carbon cycle. If DMS exists in measurable quantities on K2-18b, the most conservative interpretation is that some unknown geological or chemical process is mimicking life. The bolder hypothesis, of course, is that the planet hosts actual biological activity. To evaluate such possibilities, scientists must tread cautiously. Astrobiology, the study of life beyond Earth, is a discipline that relies heavily on inference, modeling, and indirect evidence. It's one thing to detect methane or carbon dioxide, which can result from volcanic activity or non-living chemical reactions. It's quite another to identify a compound that on Earth is exclusively produced by life. Still, even cautious optimism can be transformative. The presence of DMS does not confirm life on K2-18b, but it radically elevates the planet's profile as a target for continued research. It urges space agencies, academic institutions, and private space enterprises to prioritize future missions that can follow up on these findings. K2-18b's status as a sub-Neptune, larger than Earth but smaller than Neptune, adds another layer of mystery to its profile. Unlike Earth-like rocky planets or gas giants, sub-Neptunes may contain thick hydrogen envelopes above layers of high-pressure water or exotic ices. This unique internal structure challenges existing models of planetary formation and raises intriguing questions about the diversity of habitable environments. What if life doesn't need to evolve on rocky Earth-like planets within nitrogen-oxygen atmospheres? What if vast, warm water layers beneath hydrogen-rich skies can provide the right conditions for microbial or even complex life to emerge? Such considerations expand the boundaries of what scientists consider potentially habitable, pushing the search for life far beyond the narrow criteria originally defined by our own planet. Moreover, the orbit of K2-18b around a red dwarf star brings additional challenges and opportunities. Red dwarfs are the most common type of star in the Milky Way galaxy, making up approximately 70% of all stellar bodies. Their abundance and long lifespans make them prime candidates in the search for exoplanets. However, red dwarfs are known for frequent flares and high levels of ultraviolet radiation, which could potentially strip the atmospheres of nearby planets or sterilize their surfaces. The fact that K2-18b maintains a stable atmosphere in this context is remarkable. It may imply the presence of magnetic fields, atmospheric replenishment processes, or other protective mechanisms that help retain the planet's habitability. These protective features are essential, especially if life is to survive long-term in such volatile stellar environments. Astrobiologists are also exploring how microbial life could evolve under the thick hydrogen atmospheres of planets like K2-18b. If the oceans are warm and nutrient-rich, similar to Earth's primordial seas, then extremophile life forms akin to those found near hydrothermal vents on Earth might not only survive, but thrive. These vents, located on Earth's ocean floors, host entire ecosystems that rely not on sunlight, but on chemical energy, proving that life can exist in conditions far removed from traditional expectations. If similar environments exist on K2-18b, the biological implications could be staggering. Not only would it reshape our understanding of life's versatility, but it might suggest that life is far more common in the universe than previously thought. To explore these possibilities further, astronomers are already discussing the next steps. Continued observations with JWST will be critical, but future missions could go even further. Concepts for space-based observatories that can directly image exoplanets, such as the proposed Habitable World Observatory, HWO, or the Large UV Optical IR Surveyor LUVOIR, are being seriously considered. These missions would offer even greater resolution, enabling scientists to study surface features, cloud structures, and seasonal changes on distant worlds. Combined with artificial intelligence tools to sift through data and identify subtle patterns, the future of exoplanetary science looks extraordinarily promising. Meanwhile, back on Earth, the public's imagination has been captured. The discoveries surrounding K2-18b have been widely covered by media outlets, science publications, and educational platforms. School children learn about exoplanets in their classrooms, amateur astronomers follow transit timings online, and science fiction writers find fresh inspiration in the idea of vast oceanic worlds orbiting distant stars. This cultural resonance should not be underestimated. Throughout history, astronomy has often played a key role in expanding humanity's philosophical and existential horizons. Copernicus showed that Earth is not the center of the universe. Hubble revealed the existence of galaxies beyond our own. Now JWST may be helping to show that we are not alone. In the realm of planetary protection and ethics, the discovery of potential biosignatures on K2-18b also raises complex questions. If future missions were ever capable of sending probes to such planets, a prospect still many decades away, how should we ensure that we do not contaminate those worlds with Earth-based microbes? What responsibilities do we have to hypothetical alien ecosystems? The search for life beyond Earth is not only a scientific endeavor but a moral one, requiring us to consider our place in the universe with humility and foresight. These considerations echo the foundational questions of science, philosophy, and even theology. Why are we here? Are we alone? If not, what does that mean for the future of humanity? Interestingly, the very notion of habitable is being redefined as we expand our focus to include exotic worlds like K2-18b. Traditional metrics like Earth similarity indices may no longer suffice. Instead, new classification systems are emerging, systems that take into account the presence of volatile gases, surface temperature ranges under thick atmospheres, the chemical composition of clouds, and the interaction between stellar radiation and planetary magnetospheres. These nuanced criteria offer a more flexible and comprehensive framework for evaluating exoplanets. In this context, K2-18b may not be a rare exception, but part of a new category of habitable, or at least biofriendly, worlds. Additionally, the detection of multiple gases on K2-18b serves as a case study in the importance of synergy between space and ground-based observations. While JWST provides unmatched sensitivity, Earth-based observatories like the extremely large telescope YELT or the 30-meter telescope TMT could supplement its findings with higher frequency monitoring and adaptive optics. This coordination enables researchers to cross-check their conclusions and refine models over time. Collaboration among nations, agencies, and scientific disciplines has become the hallmark of modern astronomy, a field where the collective pursuit of truth transcends borders and ideologies. K2-18b also exemplifies how one discovery can generate cascading scientific investigations. Already, its atmospheric data is being compared to that of other promising exoplanets like TRAPPIST-1e LHS 1140b, and GJ 214b. Researchers are using comparative planetology to better understand how different combinations of mass, composition, and stellar proximity affect habitability. These comparisons help scientists develop predictive models that can be applied to future candidates. Over time, the accumulation of data may reveal statistical trends, patterns that could indicate how common life-friendly planets really are. Furthermore, the search for life on K2-18b reaffirms the importance of maintaining long-term investment in space science. Projects like JWST take decades to design, build, and launch. They require international cooperation, political will, and sustained funding. Yet the results, such as the ability to detect potential life signs across interstellar distances, are nothing short of transformative. They offer humanity a return not just in scientific knowledge, but in existential insight, technological innovation, and shared inspiration. Ultimately, the story of K2-18b is not just about a distant planet. It is about us, our questions, our methods, our tools, and our unyielding curiosity. It is about the drive to explore, to understand, and to reach beyond what is known. As we refine our instruments and deepen our understanding, we move closer to answering some of the most profound questions ever asked. Are we alone? What is life's destiny in the cosmos? Could it be that on a planet 120 light-years away, beneath a hydrogen-rich sky, and across vast alien oceans, life is stirring in the deep? And so, the journey continues. With every photon captured by the James Webb Space Telescope, every molecule identified, and every hypothesis tested, we take another step into the unknown. K2-18b is only the beginning, a gateway to a universe filled with possibilities. The road ahead is long and the